Barges shoulder up to a brand new seawall, cranes threading steel over a horizon that used to be nothing but waves. Under that clean geometry hides the problem that decides everything. A waterlogged seabed that squeezes, creeps, and slumps when you load it. Crews fight it with drains and vacuum to drive water out, and with a quieter trick that keeps runways straight even as the island settles. How do you lock a floating feeling island to a runway that must stay perfectly flat? That is the question that drives every decision on site. The workyard is the ocean itself. Pipelines snake from dredgers to a growing shoreline armored in rock. The horizon is cut by a new engineered edge. The controlling constraint is brutal and simple. Soft, saturated seabed versus the rigid tolerances aircraft demand. Miss that balance and you don't just crack pavement, you shut down operations. Across this site, one sequence runs like clockwork. Aggressive ground improvement, live sensors watching movement, and a closed, armored perimeter that keeps the ocean from undoing the work. That's the path from open water to an airfield that stays within tolerance, so people and cargo can move predictably every day. The airfield plan layers runway capacity and a large terminal footprint onto mainland, but if those surfaces shift, safety margins vanish. If ground improvement lags, schedule and cost explode. To win both stakes, you must stop differential settlement fast. Permits and environmental windows add pressure on method and timing. The mission is clear, the margin is thin, the ground has to be engineered before anything heavy arrives. Site investigations pulled back the curtain. What lay beneath were soft marine clays, silts and organics, deep marine deposits that compress under load. Reclaimed fill starts saturated and weak. Left alone, it consolidates slowly and unevenly. Satellite radar and on-site gauges tracked settlement across the growing island, flagging hotspots that moved faster than their neighbors. Those maps, refreshed as placement advanced, warned where a future runway might tilt or where a taxiway joint might open. Given that map of movement, the question becomes, which ground fixes reach deep enough, fast enough? The logic of the design is simple when you say it out loud. Make land. Make it stable, make it maintainable. Civil works shape the footprint and armor the edge. Ground improvement stitches and stiffens wet soils. Deep foundations carry heavy buildings to competent ground below. Pavements are layered and tuned to flex predictably. Coastal defenses absorb storm energy and prevent scour. The goal is control. Control differential settlement through overlapping fixes and continuous sensing. The interfaces between those layers are the real failure modes, so keeping them aligned while the ground moves becomes the central engineering problem. First, you build the job site. Temporary causeways, trestles, and laydown decks turn open water into controlled access. Then the sequence starts. A cutter suction dredger chews seabed and pumps slurry through floating pipelines. Booster stations keep pressure up while discharge spreads fill inside containment. Weather windows and routing bottlenecks threaten cadence, so crews split flow to parallel discharge points and tune pump staging to keep the island growing. That gives you land fast, but like a wet sponge. The clever part comes next. How to squeeze water out and lock the new mass so it can carry terminals and runways. Speed consolidation with a toolbox of methods. Prefabricated vertical drains shorten the path for pore water to escape. Surface vacuum preloads pull water out and accelerate settlement. Dynamic compaction hammers near-surface layers to densify fill and open drainage pathways. Where soils resist, electroosmosis nudges pore water toward drains with electric fields. Heavy buildings bypass risk with deep piles that transfer loads to competent strata below the soft zone. Instrumented test areas and settlement plates prove improvement before full loading. And woven through it all is a quiet trick, designing an embedded remediation and active releveling so small differentials can be corrected without shutting the airport for long. When you move from ground improvement to paving, the sequence becomes intensely controlled. Survey crews set tight baselines that anticipate post-construction settlement and, where needed, build surfaces high against predicted consolidation profiles. Subgrade is shaped, treated base placed, then concrete or asphalt courses laid to flex in a controlled way under gear loads. Joints, edge drains, lighting ducts, and shoulders are detailed to manage movement and keep water out. Fiber optics, settlement beacons, and strain gauges are embedded into slabs and tied to a live dashboard. Straight edge and profilograph checks certify smoothness and elevation against aviation limits before each bay opens. The loop repeats: set out, build up, connect, instrument, verify, paced by batching plants, prefab edge elements, and parallel paving lanes. If sensors spike on a new slab, operations can close a lane, inject grout beneath, re-level, and retest before the defect becomes a safety issue. Placing the coastal caissons that close the perimeter is choreography in moving water. The trench is pre-dredged to line and level, the bed verified, then the caisson floated in under tug control. Moorings and winches police drift while real-time GPS and surveys hold position. Ballasting sinks the caisson into place. As it kisses the bed, divers and multi-beam scans confirm seat and tilt. The interface is grouted and armor placed to break waves and prevent tow scour. Strict wave and current thresholds govern the operation. If motion exceeds limits, you deballast and reset. Closing the perimeter flips the challenge from make site to keep it, and once the island is enclosed, logistics become a sprint. Bulk fill flows by pipeline, piles and rebar cages ride in by barge on marine windows, and just-in-time delivery suits bulky prefabricated pieces to tight lift slots. The site runs like a floating factory and everything is interdependent. Break a pipeline and paving pauses, crews idle, and costs climb, so routing redundancy and rapid repair kits stand by. Verification gates stop bad work from reaching operations. Visual inspections, non-destructive testing, load and integrity tests, and embedded sensing baselines tie every material to a map location. When sensors flag an outlier, the path is scripted. A fiber spike triggers targeted excavations or ports, geopolymer grout is injected, and the work is retested to acceptance. Traceability and sign-offs link field engineer, independent checker, and client, so each step is accountable. Monitoring feeds straight into operations. Sensors stream to dashboards with alarm thresholds and trend lines. Controllers open intervention windows before limits are crossed. Critical systems are redundant by design. Dual power feeds, looped communications, parallel pumps, and isolated service corridors for hot swap maintenance. When a dashboard blinks, crews schedule a maintenance window, relieve pressure via drains, verify with sensors, and return the surface to service before the morning push. Commissioning happens in 3 phases. Prove components, run subsystems, then test an integrated airfield with controlled movements and preset hold points. Predictive monitoring is the payoff. Targeted re-leveling with grout injection and built-in jacking points lets crews true surfaces without wholesale rebuilds. Opening the airport is the start of a plan, not the finish. The build sits beside sensitive marine habitat, so methods had to cap suspended sediments and reduce noise, with monitoring required by permits. Dredging plans were adapted to avoid resuspending contaminants where mapped, turbidity curtains and timing windows reduced impact, and community programs funded habitat offsets and shoreline rehabilitation. Risk and responsibility follow the shoreline. Contracts share performance risk among builder, operator, and public authority, and permit-driven redesigns sometimes forced method shifts midstream. The team's big cost control choice was strategic. Designed for maintainability and continuous monitoring, so small, predictable fixes beat large, surprise overhauls. Lifecycle promise is simple. Scheduled inspections, embedded sensing, and modular repair keep tolerances in bounds. Crews cycle through pavements, armor, and utilities on known intervals. Grout injection and jacking points re-level slabs. Modular armor units swap out as they wear. Corrosion, scour, fatigue, and fouling never stop. But neither does the plan. In the end, what looks like a runway on the water is the product of relentless detail. A perimeter that holds back the sea, soils that are coaxed and stitched and anchored, pavements instrumented to tell their story, and teams ready to intervene with minimal disruption. The quiet work of monitoring and small scheduled fixes is what keeps aircraft rolling, day after day.